least the few who survive. So I'm a little behind schedule, so I'm actually going to deviate from what it says the plan is online. I want to tell you about how, for real, you go from, so turn cube in this Burnside category B into a cube of spaces, spectra. Then I think I didn't say anything about mapping cones, so let me say a bit about mapping cones. Let's have color. These two, this finishes the construction of the Khovanov spectrum. So this invariant that we've been building, that's by the time I do this, I finished doing it. Okay, great. And then 3, I'm going to talk a little bit about homology operations, particularly Steenrod squares. I think 1 and 2 is going to be about half an hour, and 3 will be the rest of the time. And so I'll maybe give you 1.5 or 2 constructions, 1.5 constructions instead of the promised 4 constructions. But the homology operations, Steenrod squares, a lot of it is sort of textbook stuff, so it's easy to read about somewhere else. In particular, it's nicely in Hatcher, and it's nicely in Mosher and Tangora. There are references on the website, as usual. Next time, I shuffle the lecture a little bit. Next time, we're going to talk about using this to get some refinements of the S invariant and more concordance information. And then there's a break of several weeks again, because there's another talk in this slot, and then there's a Thanksgiving. There's a Thanksgiving, and then we're back after that. So, and the very last lecture, we'll talk about computing square 2 on Khovanov homology, unless there are requests for something else. OK, that's the plan. Questions? Excellent. So let's start with a recall, because it has been some time. So what was this B? This was the Burnside category of the trivial group. OK, it has objects, finite sets. Hom from x to y. Should have put it to the left. OK, Hom from x to y is a set of y by x matrices A of finite sets. And then here you can talk about, there's an extra level of structure which made this into a 2 category. So 2 Hom from A to B. If these are both y by x matrices of sets, this is the set of y by x matrices of bijections. Let's have an example, just so I can trace something through in a minute with an example. So if, for example, x could be the set 1, 2. Y could be the set 3, 4. And A would then be, let's see, y by x, so 3, 4, 1, 2, maybe A, B, empty set C, D. I'll continue using this example, but I'll sort of in advance advertise that as we go on, I'm going to go back to conventions. Going to go back to my example of the cube of resolutions of the 2-component unlink. So we were using the Khovanov complex there, and the cube of resolutions there looked like this I can presumably even do that without looking. This this. It's plausibly even the right conventions. This. OK. Oh, what the heck, let's write out some of the structure we had here. So this gave me a functor to a cube in the Burnside category. Let's write out some part of that also, which we did last time. So here are the sets. So 1, here we have 1 and x, and also x and 1. Here I could have 1 and x, x and 1. And here maybe the first entry will be the label of the inner circle. Here the first we label the outer circle. Here's x. Everybody lost? These are Khovanov generators. So I'm telling you a cube in the Burnside category. And my cube is at the moment, at the level of objects, it's the set of 1, the set of 1x, x1, the set of 1x, x1, and the set of x. These are just some of the generators in the Khovanov cube for this. Okay. And in the differential, these were both terms. These are all terms in the differential of 1. And these all go to x. And we were recording that just by choosing a one-element set, matrices of one-element sets. So for example, maybe I'll call, there's no way I'll stay up with my notes. Let's go from the top down. So let's say this is A, B, C, D, E, F, G, H. And then these are really boring matrices so far, like this is the matrix set of C, set of D. This is the matrix set of A, set of B. Set of E, set of F, and set of G, set of H. Sorry, Luya. Yeah. How bad is the green, actually? Can you guys see? Green is bad, good? Bad. I'll stop using green. It's too late now.
Is that x is that x different from the x in the previous spot or is it the same? The x 1, 2?
That's completely different x.
Okay, good.
Thanks, Peter. Good question. Totally different x. Nope, that's great. And now we ask, does this square commute? This is all review from last time, but it didn't make any sense last time, so let's try again. I mean, it wasn't wrong. I just acknowledging confusion. Does this commute? Well, if I multiply these two matrices, what do I get? I get a 1 by 1 matrix. I'm going from a one-element set to a one-element set. The 1 by 1 matrix for multiplying here is, I'm capable of doing this, the set of AE, comma, BF. And here, if I go instead over and down, the 1 by 1 matrix is CG, DH. AE really stands for the pair A, comma, E. There's the product of sets is used. Nobody can read that. Good.
We saw you write it, though.
AE. I just left off some parentheses and commas. Thank you, Luya. The people on the video can't read anything, I think, so I don't have to worry about them. You guys are the only people to worry. And the answer is, well, commutes, it doesn't commute. This set is different from that set. But it commutes in the sense of I can choose a bijection between these two sets. So you're going to tell me you can't read the red either.
No, it's beautiful.
And I gave you a mechanism for choosing that bijection because somebody asked last time, I think. In this here diagram, these are where the edges used to be. If I go along the edge and I turn right, I arrive at this edge, this piece of the diagram, and I walk along here and I turn right on that part, or this piece. And if I walked instead down along this, I would turn right, I would get there. And if I walked like this and turned right, I would get there. And so when I write 1x, so 1x, this was the case that this segment was labeled 1. Okay, and here, 1x, also this segment is labeled 1. So these are sort of matched up, this 1x and that 1x. And I didn't mean to go over this again. 1x was the AE part. So the AE part is where 1 and x were matched up. And the CG part was the 1x, sorry. And so these two are paired in the bijection, and the complementary two are paired in the bijection. So the short doesn't matter how that worked. I mean, it matters, but it doesn't matter for these talks. Somehow using the geometry of the plane and like the right-hand rule, I've had a way of choosing a bijection there. Okay, yes?
How unique is this? How forced is this choice?
What a great question. Well, I could have turned left instead of right.
But you
That's-
couldn't have sometimes chosen right or sometimes chosen left.
Never say never. This is the only way I know to do it. This is probably the only way to do it that doesn't rely on some more decorations than I've drawn. But I don't promise the only way to get an odd invariant. OK. And now I'm supposed to somehow turn that into a diagram in spaces. So let's talk about going from the Burnside category to spaces. So on objects, I'm going to do something really simple. Here, this turned into z squared when I was doing Khovanov homology. So these were, it was the free abelian group generator are these. And the space level version of that is just going to be a wedge of spheres. So object x is going to turn into, let's call this f, is going to turn into the wedge sum over x and x of a sphere. So here I'm going to fix some integer n, which I'm going to think of as large. And I'll get back to how large in a minute. You know, or if you mysteriously are comfortable with spectra, this is like the wedge sum over x and x of the sphere spectrum. OK. Here, suppose I had a from x to y. So I wanted to find what is f of a. So that should be a map from f of x, which is the wedge sum over x and x of Sn, to the wedge sum over y and y of Sn, which is f of y. So how do I do that? Remember A, what is A? A is like a matrix of sets A, Y, X, where X is in X and Y is in Y. Embed the union over Y and Y of A, X, Y into, sorry, A, Y, X, try again, into the sphere corresponding to x. OK, notation. I have one sphere for each x. So this is just the sphere corresponding to x. So I'm going to do that. We're going to start with the simple example. So here, f of x was a wedge of two spheres. Here's a sphere, and here's another one. And this is sphere 1, and this is sphere 2. Y is also a wedge of two spheres. Sorry, f of y. So this is f of x. Here's f of y. Here's sphere 3 and sphere 4. OK. And what I've said is embed A into f of x. So let's see. That means A, B, and say C. Those both go to the first sphere, and D goes to the second sphere. Okay, why I've done this not clear, but I claim at least so far what I've done is supposed to be clear. Questions? Okay, I'm in the middle of construction, so I don't blame you.
Pick n just at the beginning of the day.
Just at the beginning of the day. We're going to see how big n needs to be later. That's a great question. So now, a neighborhood of the union over y and y of ayx, that's just dn cross ayx. Again, union over y and y. So let's draw a neighborhood in some color. How about orange? So here's a neighborhood. So I can now map the wedge sum over x and x of Sn, n. How to do this first. Let's consider the wedge sum over x and x of Sn mod the complement of this neighborhood. So let's just do one x at a time. I just don't want to have these wedges. Let's just do that. Sn sub x maps to Sn sub x mod Sn x minus this neighborhood of y and y of axy. So that means I've taken everything that's not in these orange parts, everything out here, and I've collapsed it to a point. Oh, that is just the wedge sum over y and y, the wedge sum over axy of Sn. Almost, yeah. So right, I've got one copy of one. So this is now mapped to 3 spheres. The sphere A, the sphere for B, and the sphere for C. And now, as Peter said, this maps in an obvious way to the wedge sum over y and y of Sn just by taking the identity map to the corresponding y. So this sphere A maps over to 3, the sphere B maps over to 3, and the sphere C maps over to the sphere 4. Question so far? So I've defined a map. You know, I've done it for each x because wedge sum is like a coproduct. This has defined it for the whole wedge sum. And now I'm going to point out that Princeton has discovered Japanese chalk technology, but there's also Japanese eraser technology. No, it's not magnetic there. What was I going to say next? I made a choice. This depends on a choice of embedding. However, if n is big, all of the embeddings are isotopic. So how big is big? 2 at the moment. So if n is bigger than or equal to 2, all embeddings are isotopic. So that tells me that the map is well defined up to homotopy. Map f of A is well defined up to homotopy. In general, so the set of embeddings is n minus 2 connected. So if n is at least 3, all of the choices of homotopy are homotopic, and if n is at least 4, whatever the next stage of that, and so on. So this becomes more and more canonically homotopic as n increases. So more and more canonically homotopic as n increases. Let's go back to our second real-life example. Okay. So here's our real-life example. I'm going to erase, I need the space, so I'm going to take over the middle boards again. But this, let's work over here. So let's try to draw out what this diagram turns into in the Burnside category. So at the bottom left, I have one generator. I'm just considering this generator X. So I have a sphere here, Sn for the generator X. Here, I had two spheres. Of course, when I'm drawing n equals 2 because that's what I'm good-ish at drawing. So here's Sn1x and Snx1. And here I've got two spheres again. Let's make them a bit bigger. Sn1x and Snx1. And here I've got one sphere. Make it a little larger just because I'm going to use that in a minute. So here's Sn1. OK. And this correspondence, let's see, the bottom edge was G and H. And to get the maps, I embedded G over here and H over there. And to get this vertical map, I embedded, what were those? Those were E and F. And I embedded, let's say, E over here and F over, and F over here. And finally, for the maps out of 1, I had to embed A, B, C, and D. So let's just say I embed A, B, C, and D. OK, so the map down, a neighborhood of E goes to this sphere, and a neighborhood of F goes to this sphere. And similarly here, a neighborhood of G goes over there, and a neighborhood of H goes over there. And the complement goes all to the base point. And here, a neighborhood of A, where did A go? A was going leftwards. So a neighborhood of A, I think, went over to there. A neighborhood of B went over to there. And a neighborhood of C went over to here. And a neighborhood of D went over to there. Does this square commute? If I go over and down, what goes where? Well, there's a little ball inside here corresponding to the preimage of E. And that much smaller ball goes to this ball, which goes to this sphere. And similarly, there's a ball inside here corresponding to the preimage of F. And that goes to here, which goes to there. And going over and down, everything else that's outside these two little tiny red disks, tiny and invisible to Louis are red disks, goes to the base point. If I go down and over, I had a disk G here and a disk H here. And everything that's outside those two disks goes to the base point. To get a homotopy between the two ways around the square, two ways around the square are not equal, right? Just not equal. But they are homotopic, and to get a homotopy, what I need to do is I need to tell you how to move around these 2 points to become those 2 points. There are lots of ways to do that in this dimension. If n was big, there would be sort of a unique way, except I would need to tell you whether this is supposed to move around to become that one or to become that one. Right? Those would give me different maps. But once I tell you the 2 morphism in this category, the bijection of matrices, bijection of sets, then I've told you essentially canonically, if n is big, how to do this. OK, so now, we had a cube, 2 to the whatever number of crossings to the Burnside category. You get a cube 2 to the crossings to spaces by doing this construction. It's certainly homotopy commutative if n is at least 2. And it's better than that if n is big. If n is big compared to C, like it's at least C plus 2, you get what's called a homotopy coherent cube. And now you want me to tell you what a homotopy coherent cube is, but it's just a formula. I mean, if I tell you, I'm just going to write down a formula, and instead I put it in the homework. So if you want to see definition, it's just a couple of lines. It's written down in the homework. Great. That's the end of the part 1 of this talk. Questions?
I don't know if it's important, but is it important that you put F on the other sphere?
Is it important that I put? It is important that I put that. Yes. Why is F on the other sphere? E was sort of this one x multiplying to be x. F was this x1 multiplying to be x. So F is like the degree 1 map from this sphere to that sphere. So this came, I said, embed this into Snx. And it's what? This x. X is plenty too many rows, but this x is which sphere it's in. Good.
This is perhaps going back a bit, but is
Please.
the degree 1-ness of the map coming from the fact that there's like one element F there, or are we just choosing?
That's right. So all of these, all the maps from here to here and here to there and here to there and here to there are all degree 1 maps. And that's because, like, to go from here to there, you collapse everything except this one disk, and this one disk is mapped by the degree 1 map. But that oneness is indeed the fact that this is a 1-element set here. If you had a 3-element set, it would be degree 3. It's always positive, I mean non-negative for the way I've constructed things. And the 1 is capturing that if we go way back, in the Khovanov differential, this occurs in the differential of that with coefficient 1, and this occurs in the differential of that with coefficient 1. Good.
Wait, but we did coefficients mod 2, right?
I think I did. Did I not? Maybe I didn't do integer. Maybe I didn't talk about signs.
Okay.
It's actually it's plus or minus 1 over z, and in the cube itself, it's plus 1 over z. That's a great objection. I probably didn't talk about signs. You're absolutely right.
Sorry, could you say again how you get the homotopy between
Yeah. To specify the homotopy, I need to specify a family of embeddings that starts with this pair. It's with this pair of points and ends with this pair of points. Just inside this sphere. Yeah, that's right. That's right. This is some very primitive version of a Pontryagin-Thom construction, which only helps if you're comfortable. Like if you've seen that before somewhere else, then that's maybe a useful way to think. But again, yeah, I just embedded those and these, and I need an isotopy that takes this one to G and this one to H. And in this dimension, you could braid them around each other, do something complicated. There's like lots of interesting homotopies. But if I went one dimension up, there wouldn't be. There'd only be sort of one homotopy up to homotopy. More questions? What else? Okay. Mapping cones. This will be easy and short, and then we'll talk a little bit about cohomology operations. It's ridiculous. The additional information is this information about turning right. And that's the additional information. That's encoded in the homotopy. It's encoded in knowing that this point is supposed to go to there, as opposed to that you're supposed to move it around to there. I mean, well, so what is the homotopy is, if you thought that we were doing some sort of Floer theory, so we had, the edge maps were counting moduli spaces of curves, then this homotopy, that's a map, that's an interval, right, or a pair of intervals, right, this interval and that pair of intervals is the one-dimensional moduli space. So this homotopy is some simple case of counting a one-dimensional moduli space. And it turns out that you can extend all of this to higher dimensional moduli space in an essentially trivial way. So all the information was contained in what things are paired up as the endpoints of the one-dimensional moduli spaces. It's a little bit ridiculous. More questions? That's the language that's the language we originally did the stuff in, of course. More questions? Okay, cones. Cones are easy. So given f from x to y continuous, the cone of f is just 0, 1 cross x, disjoint union y, mod. I'm going to collapse all of 0 cross x, so 0 x is equivalent to 0 x prime for all x, x prime in x, and 1 x is equivalent to f of x. So I don't know. So if I had this mapping to there, then you just take the target and the source times 0, 1, and you cone off that other end. If I have a square, so given this was for just a one-dimensional cube, if I had, say, x 0, 1, x 1, 1, x 0, 0, x 1, 0, I don't know, alpha, beta, gamma, delta, then, and suppose this commutes, then I can look at the cone of beta and the cone of alpha. What am I doing? I had a cube of spaces. Now the question, I didn't promise you a cube of space. I promised you a space whose homology is Khovanov homology. So this is how to go from the cube of spaces to a space. Okay, and there's an induced map from cone of beta to cone of alpha. Well, how was that? Cone of beta was 0, 1 cross x 1, 1 disjoint union x 0, 1, and this was 0, 1 cross x 1, 0 disjoint union x 0, 0 in both cases with some gluing.
Does this square commute or homology?
Suppose for the moment it commutes. Then you just take 0, 1 cross delta disjoint union gamma. I'm going to erase my little schematic so you don't get too much in the same place. So that's so now I've got a single space. So I took cones one way, and then I took cones vertically the other way. And now you say, but my square didn't commute. It a little bit better than homotopy commuted. So if, well, it commuted up to some coherent the homotopy was part of the data. So if instead I had that gamma circle beta is homotopic to alpha circle delta O. So exercise this map respects the equivalence relation. Right? You need to check that I actually wrote down a continuous map there. If instead they're just homotopic, then the exercise, so if instead this, then the exercise this doesn't respect the equivalence relation. But it's very easy to fix. So instead, so let's say they're homotopic via homotopy H. You take 0, 1, sorry, you take 0, 1/2 cross delta union H on the interval 1/2, 1, and then union gamma. So you just stick in H. You speed up. You just stick in H using part of that interval coordinate, and then you get a well-defined map, and you take its cone. And again, an exercise to check that that works, and this extends to higher dimensions, higher cubes, via an easy-ish formula. Meaning, if you wanted to write the formula, well, you could look it up somewhere, but you can spend a matter of a couple hours figuring out exactly what it was supposed to be. You do a few more examples, and it's clear how it goes. OK, that was the end of mapping cone. So now we have a space. You just do this mapping cone of the cube, and you have a space. That's the end of the lecture from 2 weeks ago. So I'm going to switch to cohomology operations. Any last desperate cries for help?
Is there some subtlety if you want to define space point actions as mapped from second subdimension?
Is there?
Sorry, maybe it shouldn't be second, just the map.
Suppose I wanted to define a base point action on this space. You can do that. Are there subtleties? I don't know. What's a subtlety? No, there are no subtleties, because your base point action is just a restricted piece of a. You do a, I want the base point action on the trefoil, merging there. You just stick in an extra little crossing, and you look at this cube, and now you look at a sub-piece of this cube, and that's your base point action. So it's no harder than doing this. You could then ask how well defined the base point action is, and that's a little complicated. Yeah. More questions? OK. I think I'm going to do a little bit of very standard textbook cohomology operation stuff, because I'm not sure. I mean, some of you have, I'm sure, read this or seen this somewhere before and will be bored. But I'm then going to reference these in the next lecture, and I want you to know what on earth I'm talking about generally. And then I'll talk about explicitly computing these operations, which is a little bit more interesting to more sophisticated people in the last lecture, if that's what we do. So the rest of the talk, for the more advanced members of the audience, you can just heckle. A homology operation is a natural transformation. I'll say what I mean by that. Hn of x r to hm of x s. These are just coefficient groups. So where by natural I mean given f from x to y. Oh, let me give this a name. Let's call this eta, which is a sort of traditional-ish name. Eta. So given f from x to y, I can write a diagram hn of x r, hn of y r. This is f upper star. Eta takes me to hm of x s, and f upper star to hm from hm of y s. Okay. Y. Huh?
That's a commutative path.
Well, it would be commutative if I wrote the eta. Thank you. I said you could sit there and heckle, so I'm pleased to be proved correct. 3 reasons. There are lots of examples. I will give you some examples in a second. 2, they're easy to understand. Easy, ish, to understand. I will explain in what sense that's true in a second. 3, they have applications. I won't explain that at all, but we'll see some applications in the next lecture, although this is a very ahistorical approach to applications of cohomology operations. So examples. Eta equals the identity from hn of x r to itself. I've been working with Dylan Thurston now for something like almost 20 years. So that's a good first example. 0 is another good example, but then it's not clear whether the target was hn or hm or r. So anyway, 0 is going to actually turn out to be an important example next lecture, but fine. Eta of x is x cup x. This is a map from hn of x r to h2n of x r. I guess R had to be a ring for that to make sense. You could just take Z. Here's the, there's one more before two more examples. So one more example. If I look at this exact sequence of abelian groups, take any short exact sequence, but for example, this one is multiplication by 2. This gives me, by the snake lemma, a long exact sequence in cohomology. To hn of x z2 to hn of x z4 to hn of x z2 to hn plus 1 of x z2, etc. And this connecting homomorphism beta is another famous cohomology operation. So beta is a cohomology operation. It's called a Box-Steen homomorphism. Well, all of the arrows in the sequence are cohomology operations. These are just not such, the others two are not so interesting. Fine. And proving it's natural is maybe a good exercise if you're doing, first-year algebraic topology. It uses naturality of the snake lemma. And computing some examples. OK. I'm interested in other examples than these, but I'm going to, in some sense, tell you all examples. Maybe I'll tell you what a stable cohomology operation. So a stable cohomology operation, that's one that commutes with the suspension homomorphism, but that doesn't quite make sense. So is a family eta n from h n of x r to h n plus k of y, of x s, k is fixed, such that of cohomology operations, so family of cohomology operations, such that this commutes with suspension in the obvious sense. So hn of x r, hn plus k of x s, h n plus k plus 1 of sigma x s, h n plus 1 of x s. This is eta n. This is eta n plus 1. Those are isomorphisms. This commutes for all n. So again, that's a cohomology operation which commutes with the suspension isomorphisms. And in our examples, this is stable, this is stable, and this is not stable. It doesn't even have the right form to be stable, so how could it be? OK, so the example. So the easiest to understand, so recall k of gn, k of, that's fine, gn. This is an Eilenberg-MacLane space. Is your favorite CW complex with pi I of k of g n equal to 0 if I is not n and g if I is equal to n. And the reason that these are important is a theorem that I don't know the attribution of, that hn of x with coefficients in g is canonically isomorphic, so right, equal to the set of homotopy classes of maps from x to k of g n. So this is homotopy classes of maps. And I think I want to tell you what the map that direction is. Let me remind you how that works. So that is, the Eilenberg plane spaces are what are called representing objects for cohomology. So that direction, well, if I look at hi of k of gn, this is 0 for I less than n and g for I equals n by the Hurewicz theorem. So h upper n of k of gn is hom from g to g. This contains the identity element. So that gives me an element iota in there. And the map backwards is f maps to f upper star iota. Okay. You know, in some formal sense, I'm saying everything you need to know. In fact, of course, either you saw this before or you're totally lost. This is all described nicely, though somewhat more slowly, in the Hatcher book, for instance.
The upper one is z coefficients and the lower one is g coefficients.
G. Thank you. That's a typo. Yeah, thanks. Yes, I apologize. What was I going to say next? Nobody knows. Corollary. Cohomology operations from Hn of x R to Hm of xs are in canonical bijection with the cohomology of k of Rn with coefficients in S. And the proof is easy, but maybe I'll leave that to you to look up or as an exercise so I get to the last thing I want to tell you. So this says if you want to understand, this is the answer to 2. It's easy. If you want to understand all cohomology operations, you just have to compute what are the cohomology groups of this one damn space. And, you know, you can get your hands on these spaces often and compute. So, I tried to find reference for this stuff. This was well known by Eilenberg MacLean in 1953. It is a well-known observation that a cohomology class gamma in whatever that induces a cohomology operation. It wasn't so helpful for tracking the reference. Theorem, I'll stop after I state this. Maybe due to Serre, maybe it was known earlier by Steenrod. The ring of stable cohomology operations from H star of x z2 to H star of x z2 is generated by operations I'll call SQI from Hn of x z2 to Hn plus I of x z2, I equals 0, 1, 2, etc. Some remarks. Square 1, square 0 is the identity. OK, I wrote that one. Good job, Robert. Square 1 is the Bochstein. I wrote that one also. Square 2 is new. These are not all independent. The relations are the Adem relations, which you can look up anywhere by searching for Adem relations. The word ring is confusing. At least I keep being confused by it because I'm not actually an algebraic topologist. There are two ways you could imagine multiplying. You could imagine, look, we're looking at the cohomology of Eilenberg plane space, so it has a cup product. That is the wrong multiplication. Multiplication is composition, so multiplication is composition. However, there's a very similar looking theorem of Serre on a related topic where multiplication is cup product. So like, it's sort of hopelessly confusing. The theorem is proved by computing the cohomology of these spaces using the Serre spectral sequence, at least the modern proof of the Serre spectral sequence and induction for the path loop fibration. So is not easy, but it's not particularly challenging either. Philosophy. These Steenrod squares, I'll give you a sort of explicit definition of construction of square 2 probably in the last lecture. We did square 0, square 1. There are pretty explicit constructions. I mean, the explicit chain level formulas in general. Oh, this is all explained nicely in a paper of Steenrod's, a survey paper I linked to. But the fact that this theorem means you find them all over the place. So they show up over and over and over. Because if you did some construction that gave you a cohomology operation, there are lots of those, like the first non-trivial differential on any spectral sequence, basically. Lots of obstruction theory type arguments, lots of other things. If you had some construction that gave you a cohomology operation, it had to be one of these, or at least a polynomial in these. So you sort of can't get away from them. Stable cohomology operation, stable cohomology operation. Those almost sort of true unstably also. So, you know, they show up lots and lots of places for that. And that'll help us. The reason I say the theorems, that'll help us with identifying what we say is square 2 with the usual square 2. It won't have any choice but to be the usual square 2. OK, I'll stop there. Thanks for listening.